Okay, so what we will do now, we will consider curvilinear motion. So we already studied rectilinear motion. Now we will see how to deal with curvilinear motion. So in case of curvilinear motion, in order to define motion, I need to consider a certain curvilinear coordinate. Okay, so as you can see here, you should take a certain origin, and you can say that the particle can be defined, the position of it required to know the curvilinear coordinate s. Okay, so s will represent, if you want, it will count the curvilinear distance traveled. S can be positive if we are moving in positive direction, and negative if we are moving in the opposite. Okay, so also we have to select a positive direction for S. So, and at any time, this is called the position vector. The position vector is from the origin to the particle. Okay, now the position vector, of course, will be function of time, and its direction and magnitude will change as the particle will move along the curve. So this is the most general case. In case, for example, you are moving on a circle, then the magnitude will remain constant, but the direction will be variable. Okay. So also here in curvilinear motion, we represent the displacement delta S by the variation of position. So between initial and final position, I can say that delta R vector, especially look, if you take a very small angular displacement, the arc delta S as arc of circle here, and it's a curve, will be equal in magnitude to the vector delta R. Because when you take small angles, the arc of circle will be equal to the segment. Okay, but of course, if you take large angular variation, it will not be the case. And delta R is a vector. Okay, so delta, and if I take position here, delta R will be this vector, while delta S will be the length of the arc here. Okay, so in general, when we define for small angular variation, we can say that delta S magnitude is equal to delta R magnitude. So the displacement delta R represents the change in particle position when going from position 1 to position 2. And also we can define, as we did previously, we can define an average velocity as delta R over delta T, and we can define an instantaneous velocity as V instantaneous is dr by dt. Now, similarly for the acceleration, we have average acceleration uh, and instantaneous acceleration. So for the average acceleration, it is delta V over delta T, while for the instantaneous acceleration, it's dV by dt. Okay. Now, we have two types of graphs for acceleration. We can draw the path of motion, and we can draw the hodograph. What is the difference between the two? You have that path of motion, الفector بيكون الvariable vector بيكون position vector. So for example here, if you this is the path in blue. Okay, in blue, when you take the origin, you draw the position vector at any instant. Okay, and when you join the points, you will obtain the path of motion. Then the vector velocity will be tangent to this path, because V is always tangent to trajectory. On the other hand, the acceleration in this graph will have two components, and you will see this together. So the acceleration in this case will be divided into tangential and normal components, and we will see how to divide it. So it will not be a tangent to the path. It will have one normal component, one tangential component. So this will be called AN, and we will learn together how to find it. And this vector is AT. This is in the path graph. On the other hand, we have another type of graph that can be done, which is the hodograph. In this case, the vector that we draw is the velocity. So in case at any time you draw velocity vector and you join the points, you will not obtain the path of motion because the path of motion is for position variation. Here, the graph represents variation in velocity. So this is why in this graph, since acceleration is the derivative of velocity, then vector A will be tangent to the hodograph. Okay, while in the path of motion, it will have normal and tangential components. Now, how in curvilinear motion we can deal with different types of coordinates, and we will see based on the given how to select which coordinate to work with. The first type of coordinates is rectangular components. So if I give you 3D motion, let's say, and you have a frame x, y, and z, in order for you to define your curvilinear motion, you can represent your position vector r by three components, x, y, and z. Okay? So if I give you, for example, the expression of the position vector with x function of time, y function of time, and z function of time, you can easily get the velocity vector and the acceleration vector by doing derivation. Okay? In this case, the position vector magnitude can be calculated at any instant by radical x squared plus y squared plus z squared. And the unit vector can be found by doing the vector over its magnitude. So you are well familiar now with how to get a unit vector. Now, concerning the velocity, if I want to define the velocity in rectangular components, all I have to do is to start from my definition that velocity is derivative of position with respect to time. So since velocity is derivative of r, I will derive the position vector r. So since r, for example, r is xi plus yj plus zk. Okay. So I will do the derivation for xi, and for the remaining ones, it's the same method. So here you have a number, a certain algebraic value times a vector. But because my vector is not changing, and I, j, k are fixed, because they are fixed vector, this means that their derivative are 0. So I just have to derive x. So here, if I derive this, I will get x dot, which is dx by dt, times I. And we know that dx by dt represents what? It represents the velocity along x. So by analogy, I can say that the x component of velocity will be x dot, which is the derivative of x with respect to time. The y component of v will be dy by dt, and the z component of v will be dz by dt. And concerning the magnitude, at any instant, I can get it as radical vx squared plus vy squared plus vz squared. And I can know the direction by getting the unit vector. Now, same procedure for acceleration. If I want to get the expression of acceleration, then I will start from definition. A is derivative of velocity with respect to time. So ax, the x component of the acceleration, will be the first derivative of vx or the second derivative of x, because the derivative of dvx by dt will be equal to the second derivative of x. So we derive x dot, you will obtain x dot dot. This is the symbol of derivation with respect to time. So in general, I think you are familiar with this notation. X prime is a derivation. But in particular, when the variable is time, we replace it by x dot with a point. And the second derivative, x second, with respect to time, is represented as x with 2 points, dot dot. Okay? So ay by analogy also will be y dot dot, and az will be z dot dot. And of course, for the magnitude, we use the radical formulation. Now, a small example on this. At any instant, the horizontal position of the weather balloon is defined by x equal 90, where t is in seconds. If the equation of the path is y equal to x squared over 30, determine the distance of the balloon from the station at A and the magnitude and direction of both velocity and acceleration when t equals to 2 seconds. So for example here, they gave us x as function of time and y as a function of x. And they want us first to determine the distance of the balloon from the station. This is the station at A, and I know y function of x. So knowing that x of the balloon is 18 meters, if I replace x in y, I can get y of the balloon. So y of the balloon is 18 square over 30. And to get the distance from A, all I have to do is to find the distance AB. So I will do radical of xb squared plus yb squared. I can get this distance from the station. Now, concerning the velocity, so since x is given function of time, first to get Vx, I only need to derive x with respect to time. So I say that Vx is x dot. So the derivative of 90 is 9. Then I got my x component for velocity. Now for y component, I can do two methods. We will learn together the new method before. And the simplest method is to replace x by 90, then y will be function of time, and we derive it. But sometimes this will not work, and in some problems you are forced to go over by using the chain rule. This is why I will introduce it here. What is the chain rule? The chain rule is the following. Y is given function of x, but I want dy by dt, so I want to derive y with respect to time. Because y is not function of time, I can decompose the derivation dy by dt as follows. I can write it as dy by dx times dx by dt. Okay, this is called chain rule. Because I did derivation in steps. So now I can say that since y is given function of x, dy by dx is simple to find. It's 2x over 30. So it's x over 15. So now I can replace dy by dx is x over 15. And dx by dt, it's already calculated. It's 9. So it's x over 15 times 9. This is Vy, okay? Or the second method, if you want, I can say since x function of time, I replace it by its function, and I can directly do the derivation with respect to time. So both methods are right, okay? Now, in particular, I am interested for what is happening at 2 seconds, okay? So to know what will be my velocity at 2 seconds, first I replace t by 2 in my equation. I get x equal 18, and I replace x here in this expression in Vy. I will replace x by 18. I can get the value of Vy. And once I have the x and Vy, I can calculate the magnitude of velocity. And of course, for direction, now knowing x and y components, so here I know x and y, both are positive components, so I can say that I am in the first quadrant. So this is Vx, this is Vy, and to calculate the angle, I do just, so if I want this angle, all I have to do is tangent minus 1 of Vy over Vx, okay? So this is how we get the value of theta. Now, finally, for the acceleration, all I have to do now is to derive the velocity. Since Vx is constant, then the derivative of Vx is 0. So I just have ay in this problem. And to get ay, I should derive the velocity with respect to time. Okay? So going back, if I go back to my expression, I had that Vy is y dot, okay? We got that it's equal to 2x over 15 times 9, okay? So here also I should do the chain rule. If I didn't, or I replace x by 90. So it's up to you. Let us do the second method now, since we used the chain rule before. So just you can replace x by 90 here, okay? And once you replace, sorry, it's x over 15 times. So once you replace x by 9t, you will get 81t over 15. Okay, so it's a linear variation. V is linearly varying with respect to time. So I expect that A will be constant. So if I derive V with respect to time, I get 18 over 15. And then the value will give me the acceleration AY. Now I have AY, and since AX is 0, then my acceleration vector will be vertical, and it's doing 90 degrees with the horizon. Okay. Any question on this? So we continue hopefully next time. Bye bye.